In this session, Andy and I are super excited to take you on a deep dive into how VAST's approach to retrieval can help transform your business using the power of data-infused AI.
By now, we know AI models are great at handling queries that they've been trained to answer, but the promise of AI can fall short within an organization because of the limits of how we deploy and fine-tune today's models. There are a number of reasons why fine-tuning alone isn't sufficient for enterprise AI. First, businesses work in real time, yet models are only trained on a periodic basis. To be relevant to data-driven business, AI systems need to work with the most up-to-date information. Therefore, models need to be enriched and augmented with real-time data so they can be relevant to knowledge work. This is, of course, why retrieval systems have proliferated. Second, enterprise security is not something generative AI models were designed to enforce. Permissions don't get carried through a training or fine-tuning pipeline, and like real-time data sets, permissions can also change in real time. Therefore, the systems that support AI retrieval must enforce access control in real time from the unstructured and structured data systems that they retrieve data from.
Finally, when you take a step back, it's clear that the challenge is greater than just feeding real-time data to AI models and enforcing permissions, not to diminish the complexity of either of these two efforts. But the amount of complexity associated with cataloging and indexing enterprise unstructured data using new AI tools, weaving together real-time unstructured and structured data for retrieval engines, implementing consistent access control policies across indices, and then building workflows that make this all easy for every organization to embrace AI, it just doesn't work. The whole world is new in this territory, and the organizations who are just now dipping their toes into AI retrieval are realizing that the glue code and the random tools that are used to build retrieval pipelines are not scalable enough. They are far too difficult to secure, and they are far from simple. So within this soup of complexity, we've also discovered a wide open space to bring new invention fit for purpose to usher in a new age of data-informed and real-time enterprise AI. So let's talk about the invention behind the VAST Insight Engine. But before we go deep, maybe I should explain what the Insight Engine is for you all. Insight Engine is the first application to run natively on VAST Data Platform. The system incorporates NVIDIA Inference Microservices, or NIMs, a part of the NVIDIA Enterprise AI stack that runs in software deployable on NVIDIA hardware. Together, VAST and NVIDIA are building an all-encompassing system to support AI retrieval that allows organizations to ingest structured and unstructured streams in real time, to index them using AI embedding tools in real time, and then finally to serve answers to agentic applications with real-time vector and knowledge graph search tools that work at any scale. Now, all of this happens within the enterprise security framework that comes naturally from building intelligence into the enterprise's data foundation. It's fast, it's scalable, it's secure, and it's simple. We'll share the fine-grained details when we get closer to shipping the system in early 2025, but today we wanted to spend time on the inventions that make the Insight Engine fundamentally different from other approaches to retrieval in the market. Inventions that radically change the definition of what is possible with enterprise AI. So let's talk about performance and scale. Performance at scale is a multi-dimensional problem that we need to start by breaking down the retrieval AI pipeline to understand. And then we can analyze the bottlenecks and discuss why scalability matters. Retrieval pipelines begin and end with an AI agent that can take a data request, translate it into a query, and answer with contextualized responses where either the agent can answer the data from what it's been trained or fine-tuned with, or it can go out to some external SQL engine to ask a question to a data warehouse, or agents could also retrieve answers from an organization's unstructured data. This is done by querying a bunch of vector embeddings that have been created and indexed using AI microservices. Now, these vectors describe the documents and the content that sits inside enterprise file systems and object store and stores their semantic descriptions as vectors in a vector database. But if we're going to build real-time infrastructure, where does speed matter? Well, the focus for both vector databases and data warehouses has always been on optimizing for search performance, which, for the record, is very important. But search isn't the only thing that's important when building real-time retrieval pipelines. First, in order to even understand how real-time is defined, let's look at database ingestion. Vector databases are typically only periodically updated by some embedding microservice that runs as a scheduled batch unstructured data indexing process. This workflow then stores a series of batched updates in a vector database that need to be indexed and then re-indexed as new data comes through the system. So much so that even the most real-time RAG systems only get updated in intervals of every few minutes. Compare that to the average VAST environment, where customers can be at times creating thousands of files per second or hundreds of thousands of files per second. We need systems that can keep up to that level of data intensity. The same is true for enterprise data warehouses, where message brokers are built into the front end of a data pipeline to collect and organize structured data before sending it down to some data lake or data lakehouse in some batched ETL process. Now, this is because you can't stream data natively and transactionally into a legacy data warehouse. It leaves a big gap in query engines being able to provide real-time insight. Sure, it's possible to analyze real-time event streams in your event bus, but this only gives organizations a very limited view of their data, since their real-time data can't be correlated against the rest of the data in their environment that lives on systems that are better suited for analytics than they are for data ingestion. Now, second, when it comes to querying on data, both of these systems lean heavily on data structures that are well suited for object storage and hard drive-based data lakes. And as these data sets continue to grow, it becomes tougher and tougher to build indices that fit nicely into vector database server nodes, where any search on data that hasn't been well indexed is slow, it's computationally very intense, and it's unsuitable for high performance, low latency queries. Now, third, let's consider scale. Most vector databases are new. They were rushed into the market during an AI gold rush to accelerate the adoption of RAG pipelines by augmenting chatbots with a limited amount of well-curated document data, oftentimes PDFs, to provide additional context to large language models. No system ever really envisioned needing to support trillions of vectors. And even as the most scalable databases can scale, their ability to ingest data in real time and search on data slows on an inversely proportional basis as they scale. On the other hand, the enterprise is sitting on exabytes of unstructured data that's waiting to be semantically indexed. And indexing is still in its first inning. Just think about the exponential rate of improvement we've seen with generative AI models over the last 2 years. As we deploy better and better AI embedding models to index enterprise data, the world will need much more scalable infrastructure to achieve a unified view of highly dimensional vector spaces. So both vector databases and data warehouses are poorly designed for real-time data ingestion. And they're difficult to scale and search across large spaces, and that can be even more cumbersome as embedding models improve. Why is this? Well, as we looked across the different approaches taken by vendors in the market, we always find the same root cause: architecture. Now, as you peel back the covers on any modern distributed storage system or distributed database, you'll inevitably find derivatives of a system architecture that was popularized by Google in 2003 when they released a white paper detailing a next-generation shared nothing systems architecture that powered the Google file system. This paper had a profound impact on the distributed systems landscape, and the architecture that Google laid down, where data sets are partitioned across commodity storage and database servers, is the basis for modern data computing. And while that shared nothing architecture really did help the world manage and analyze capacity at massive levels of scale, they also introduced a trade-off between scale and transactional performance. The reason for this is simple. As I grow a set of independent nodes in a cluster, the nodes need to stay in constant coordination with each other as there are changes to the state of the system. And so, as communication grows exponentially with the transactions in the system, the clusters begin to slow. The east-west traffic created by partitioning and consistency management in shared nothing systems is the principal reason why enterprise data warehouses are notoriously bad at inserts and updates. And that's why they've never been designed for real-time data analytics, because you can't just stream into them. And so that's a problem. Andy's going to talk about how we're going to solve it.
Thanks, Jeff. To build systems that can stream, index, append, and query data in real time, we had to create something entirely new. Thankfully, we got a head start in 2019 when we introduced our disaggregated shared everything, or DASE architecture, the foundation for the next 20 years of computing. DASE achieves a new level of transaction and analytical parallelism by disaggregating compute from storage, separating the logic and state layers. Stateless compute nodes access the storage layer concurrently over a high-throughput commodity network fabric, making it possible to distribute workloads across thousands of processing units that all see and consistently transact into a shared global storage volume known as the VAST element store. The element store harnesses the components of the DASE architecture to expose metadata and data structures that are designed for massive scale. A modern take on the B tree, we've implemented V trees, which have extremely wide fan-out, enabling access to any piece of data or metadata with a minimum number of hops across our backend data fabric. This creates the foundation upon which we have built the most scalable data platform that has existed. Over time, our element store has been extended. Beyond being able to simply store unstructured data in the form of files and objects, last year we implemented and deployed the VAST database, a scalable and high-performance solution for structured data in the form of rows and columns. This year, we've added even more functionality. We now have an event bus, where messages from internal functions and external producers flow directly into the platform, stored instantly in VAST database tables. We're also proud to announce that the VAST database has been extended to natively support vector embeddings and search. How are we able to put both messages and vectors into the VAST database? First off, the database is able to transact at millions of events per second, even without batching. Perfect for high-speed message queues. Next, it is ACID compliant and transactional, and indices are updated within milliseconds to support millisecond search of real-time vector spaces and knowledge graphs. Therefore, queries can be executed in constant time, regardless of the scale of the vector space. The system can search through trillions of vectors with millisecond latency thanks to our architecture that leverages low latency RDMA access for each data engine node to access data and metadata in parallel. Now that you know a little bit about what we built, let's walk through 3 distinct phases of an AI retrieval pipeline: ingest, processing, and query. To support a large enterprise retrieval workflow, the system must ingest thousands of files and objects per second. Simultaneously, there are also SQL applications persisting structured records into VAST database tables. And finally, streaming data in the form of messages from external producers flow into topics that are instantly able to be queried. These messages can also be generated within the VAST platform itself. For example, every new object triggers an event or a message, which itself may trigger another function. Thousands of files per second, which is something we commonly see, can easily balloon into tens to hundreds of thousands of events per second and hundreds of thousands to millions of database transactions per second. Not only is our platform able to keep up with this load, but it is able to do so with consistent latency. Okay, data came in. Great. Next step is processing. We're going to focus on the processing required for generating and storing vector embeddings with VAST event-driven architecture. Data can be chunked and vectorized in real time. Here's how it works. Every new file or object triggers a series of functions. For example, we set a definition of functions that can, say, look for an MP4 file being ingested. An NVIDIA NIM will first perform speech-to-text transcription. This NIM creates a text file that triggers another NIM to generate vector embeddings from the text chunks. The same happens with the file's video frames, splitting a video into sequence of frames and generating embeddings from those sequences. The scale of this pipeline can be massive, as each frame of video generates embeddings. Consider that with thousands of files coming in per second, the scale of embeddings being added into the VAST vector store can easily reach millions per second, far beyond what is achievable with traditional vector database implementations. Now, these functions aren't just reading from objects, tables, and streams. They're actually running directly on our platform within containers that take advantage of available CPU and GPU processors. Thousands of functions are constantly executing, handling tasks of all types. As ingestion ramps up, so do the number of functions that the system executes. If the load gets too high, VAST DASE architecture makes scaling easy. It's just a matter of adding more containers to keep up with demand. Okay, embeddings are generated. Time to service some prompts. So for this, we need fast response times, especially when many users and applications are performing searches. Fast access to vector embeddings is critical. Thanks to VAST's unique element store metadata, similarity and nearest neighbor searches happen in the same amount of time, regardless of the database size. Remember, this is happening while the same vector database is handling ingestion of embeddings during processing. So not only can millions of embeddings be inserted, but they are instantly accessible for search. There's more to this than just vector search, though. In order to actually generate a response, data is being retrieved by pulling from objects in the data store and selecting entries from VAST database tables. A single prompt can trigger a multitude of queries, function calls, and storage requests. Meanwhile, the platform is also generating events that power feedback loops, which enable fine-tuning of pipelines over time. All of this needs to happen quickly to ensure that every prompt is serviced in near real time, even as hundreds of thousands of users and agents issue prompts simultaneously. As you can see, the architecture makes it possible to handle a level of scale across all facets of a retrieval pipeline. Now that we've solved this, the natural question arises: how do you secure it? For that, I'll turn it back over to Jeff, who's going to walk through the challenges to security and compliance when deploying retrieval systems in the enterprise.
As mentioned, AI models are not trained to understand or enforce data access permissions. Even if they were, permissions change so much more frequently than AI models are updated. This disconnection makes it impossible to train general models with sensitive data that has any level of personal or departmental access sensitivity. So the need for better data isolation is clear. Retrieval is the first step in creating this isolation, since it's now possible to serve data through AI models without having to train data with AI models. But the act of isolating data from model training and fine-tuning isn't enough. RAG pipelines are super complicated, in part because of the fact that the systems that index your data are disconnected from the systems that store and manage your source data. Until now, there's not been an enterprise file system that's been built with a transactional data warehouse. So customers have to cobble together separate databases, separate embedding systems, and retrieval microservices, all with different file and object storage systems that they maintain. So how do permissions get enforced? Well, often authorization platforms are used for RBAC or ABAC policy enforcement. And by syncing sources with an authorization service and then syncing this with a vector database, it's possible to filter responses and enforce permissions when doing retrieval. The primary issue with this approach, of course, is that permissions drift over time. And this pile of systems that organizations need to cobble together require ACLs to be periodically re-indexed from data sources that are all disparate. And since it's very difficult to synchronize and index ACLs in real time, this creates windows of data access exposure. The reality is, if file systems could vectorize and index their own data, we wouldn't need all of this complexity of policy synchronization, since data and ACL models can be unified at the source. And so Andy's going to talk about how to do this right.
Let's start with the basics. We'll walk through a similar ingest, process, and query flows we did for the speed challenge, only now our lens is focused on security. While we are used in many large-scale HPC and AI environments, we started by building an enterprise data platform, ensuring that there is a unified security model for governing access. VAST was the first platform to unify security policies at the foundational level, enabling multi-protocol access to files and objects simultaneously. When we introduced the VAST database, we extended these policies to not only cover file and object, but also granular access to database tables. That is to say, both structured and unstructured data. Another first. To illustrate, here's a policy which defines that the user Alan can access files within the cool stuff directory in the vids bucket. He can also query tables that are placed within the vid metadata database. Multiple entries can be added to extend more access for him without having to manipulate the underlying file system or database table permissions. The beauty is, this model is also effective for vector embeddings, and as a result, vector search. How? It's quite simple. Every file, object, and table in the VAST data platform has an associated entry in the VAST catalog, and each entry contains cells which hold all the permission for a file, object, or table. Whenever a new file is ingested, chunked, and vectorized, those embeddings are stored as entries in a VAST database table, along with a pointer to the unique identifier for that file. This particular set of embeddings point to the Spider Ghost MP4 file in the Jason Home Movies directory. If we look at the catalog entry for this file, we can see that Alan does not have permissions to read it. Apparently, Jason is not ready to share the magic of Spider Ghost with the world just yet. When a vector search on this platform occurs, here's the basic flow. First off, we capture an identity token which represents the user who is performing the search. We pass the token, along with the vectorized prompt, into a cost optimizer, which chooses algorithmically which filter to perform first. One filter is for embeddings that are nearest neighbors. Once the answer space has been reduced down, the next filter is for embeddings that match a certain security filter, where the system interrogates the catalog to identify whether the token has access to the underlying resource, whether it be a file, object, or database record. Only embeddings which pass this test will be returned to the application. This approach is also effective when permissions change, as is common in enterprise environments when projects evolve, when employees change departments, or as contractors come and go. From an administrator standpoint, it's as easy as binding the VAST system to an enterprise directory service, such as Active Directory, defining appropriate policies, and providing relevant endpoints to users and applications. Access to any type of data will pass through this unified model, and every action is audited and captured in a scalable audit environment, which, by the way, is back-ended by a VAST database table. So detecting anomalies or suspicious behavior is built-in and trivial, even at massive scale. The key to all of this is that the VAST platform is authoritative for access to data of all types while maintaining lineage between entities, as is the case with the scenario I just walked through. Updates to any metadata structure are atomic, and our DASE architecture ensures that all compute nodes, and as a result, all applications, see the exact same state that includes all security and compliance data, including permissions, policies, and identity mappings. Keep in mind this is only possible because we are not integrating a bunch of independent systems with independent access control mechanisms into a RAG pipeline. VAST has built a unified data platform with a unified security layer where we keep adding capability into the system versus integrating with other systems and creating complexity. So we've covered the data layer, but to bring retrieval data to life, we need to marry computation and data. This can be far from straightforward, so Jeff's going to talk about the simplicity challenge when deploying retrieval AI systems.
Thanks, Andy. Okay, so building an end-to-end data pipeline to support enterprise RAG is simple, right? All you need to do is set up a system alongside your primary file and object storage systems that can support AI-based indexing, since legacy file systems don't really handle AI parallel processing well. Then, just go and build some GPU cluster to periodically scan and create these embeddings with all the workflow orchestration to make this automatic. And then, go and build a vector database that can store and index these embeddings as well as to help build knowledge graphs. But to save money, you should tier your embeddings off to some slow object storage. Oh, and then go build an enterprise data warehouse to support your text-to-SQL queries. But to do this, you'll need to also build an event bus that captures your real-time event streams, since the data warehouse is not transactional. And then hope that you don't need to correlate the two at the same time. Oh, and then try to actually go and establish a unified policy enforcement engine that can make sure that permissions don't fall too far out of sync. And then finally, spend the next 3 years trying to tune this infrastructure so you can get as close to possible as real time, such that your business isn't continually getting served old or stale data. Easy peasy, right? Of course not. Now, different cloud-based platforms will prescribe you the easy button. Just run your pipelines on their push-button platform. All you need to do is marry to their cloud of choice, and then copy all of your data to some remote data lake that you need to process from. Simplicity has a real cost in this case. The permissions complexity problem definitely doesn't get solved, and the pipeline is far from real time if you have to copy data from your enterprise file systems to your cloud data lakes. So let's do something better. Andy's going to tell you how it all works.
Thanks, Jeff. With VAST, you get a unified data model for unstructured and structured data. Having everything in one platform means data is always in sync and current. A unified security model, ensuring that you only set policies in one place, and data, metadata, and derived embeddings are secured from end to end. We've talked about nuts and bolts enough, though, so why not just see a little demo? Let's start with real-time data in a table that can also do analytics. Here we have a stream of IoT sensor data landing in the form of messages. I can query it the moment it arrives to see the latest information. I can keep running the query over and over, and it updates in real time. I can also run an analytical report against the same table. Notice that I have hundreds of millions of records in this table, and these charts still build quickly. Okay, changing gears. Now we'll explore lineage between unstructured data and the embeddings that get generated. Each record in our vector tables contain a pointer back to the original data, as you can see when I query the table directly. Not only that, but if a file gets removed, the records in the table are pruned so that future searches will not return any results which are stale or invalid. To prove it, I'll go ahead and delete this file in the window on the left, and on the right, you can see the output of the event log showing the deletion and now showing that a function is fired to prune records that link back to this file. Let's go back and rerun my query against the vector table, and those entries are gone. And lastly, let's take a peek at the NIMs deployed on this system. As NVIDIA continues to add more models and functions to their library, they will be easily deployable directly on VAST. They can be stitched together with data manipulation and transformation functions, both bundled and tested by VAST, as well as those that you developed yourself with our SDK. So, what will you build?
As we move to a world where our work is supercharged by AI agents, and as agents start to work with each other, the potential of securely informing these agents with all of an enterprise's critical data assets is so powerful.
Business happens in real time, and for AI to drive the greatest impact, it needs to be equipped with the tools to capture, process, and feed real-time data into AI applications. To achieve this vision, we can't just get there by integrating independent systems of legacy architectures.
If you've made it this far, it's been our honor to share with you all of the fundamental innovations VAST is introducing to democratize real-time AI retrieval and data-driven artificial intelligence pipelines for all of the enterprise. Thank you so much for watching.